Okay, in this segment we're going to be looking at homework from section 3.3 for finding zeros of polynomials. And so we start with number 1, use the factor theorem to decide if the second polynomial is a factor of the first. So actually the synthetic division helps us try to factor down polynomials, which also relates to finding their zeros, which means we're finding their x-intercepts or solutions. Those wordings all go together. They're synonymous for what we're trying to do here. So we accomplish a lot of things with synthetic division. So the second polynomial, x plus 3, is in polynomial form, so we want to change the sign to -3. That's called the k value of the synthetic division. So when x is on it, x plus or minus a number, we always change the sign. So that's k. Then we use the coefficients of the polynomial, making sure they are in descending order and that no places are skipped. Here you'll see x to the third and no x squared, so we'll need a 0 there, and then 6x and -9. So we reflect those coefficients, remembering to watch out for zeros. And then we bring the first number down under the line, multiply and add, multiply, add, multiply, and add. And if you get a 0 remainder, that means yes. That means the remainder of synthetic division. It's a type of long division. If you divide something and get a remainder of 0, that means this goes into that evenly, so it's a factor of that. All right, so yes. Number 2, we're going to use that idea to factor a polynomial, and it gives us a starting point, k equals 3. Notice that I don't change the sign here. It's already in k format, so use it as is, 3. And we write coefficients. I notice here nothing skipped on them. So we bring down the 2, multiply, add, multiply, and add my way across. And I'm expecting a 0. It said it was a 0 of the polynomial, so I expect a remainder of 0. Now this is a quadratic. What synthetic division does is it divides by x to the first, like you saw in number 1, when we're dividing by x to the first. So dividing by x to the first would take down the polynomial by 1 degree. It subtracts 1 degree from the original, so it's always 1 degree less. So if it starts out x third, this is 2x squared plus 9x minus 18. It's actually a quadratic. Some quadratics are factorable, and some you have to use the quadratic formula on to solve. You'll see later in the lesson. But this one says factor, so it's factorable. So you could either from there do the reverse of the FOIL method to figure it out, or you could keep doing synthetic division and hunting for zeros. I'm going to demonstrate it with the old-fashioned reverse of the FOIL method. So I'll say I need a 2x times 1x to get 2x squared. The signs need to be different to get a -18 on the end. I'm not sure if it's going to be 9 times 2, 6 times 3, 18 times 1. I'm totally guessing, and I did miss it. You can see when I FOIL your inner and outer parts, I get 5x. So wrong. I'm trying to get a 9x. So I try again. Maybe it's 2x plus 6, x minus 3. So I can kind of foresee that doesn't pan out for me either. So I rearrange 2x plus 3, x minus 6. Let's see what happens there. So the first is still 2x squared, and the last is still -18. So those are in place. And remember, we're using the FOIL method to check this. So the first and the last should work by just trying to get the number here. The last trying to get that number. That should be good. So you only need to check your inner, that's 3x, and outer minus 12x, and see if those combine, since they're like terms to right middle. Well, I'm close. At least I've got the right number, 9. The sign is easy to get the right. You just need to switch these around and go. You check it, and you should be in business. So we've completely factored a third-degree polynomial. The answer is, since that 3 is a 0, that will be x minus as a factor. Then 2x minus 3 and x minus plus came out to be our final factoring for the quadratic part. So now if we FOILed and multiplied, we assembled that, we could then multiply back and see if our answer is correct, it should all multiply to be that. A lot of work, but that's how we would know. All right, do it again. The next one is the same type of question. I'm going to get an extra sheet of paper and see there's not room to do that there. So the next problem, we have 2x cubed, 3x squared, minus 110x plus 225. And we're trying to factor that. And to help us out, they tell us one of the zeros just to get us started. It would be really hard to just guess the first thing that works on this. So they give us a clue that -9 works. And then we put in all of our coefficients. Again, there is no places skipped on this one, so we're good to go. And I'm fully expecting this process to give me a 0. Since that was in the directions. I'm going to have to use my calculator here. 9 times 15 is 135. And the signs are alike, so it's positive. Then I use my add rules. That's 25, sorry. Add rules here. 135 and minus 110 is 25. Then 9 times 25 is 225. Good, because that's what I need it to be to add to be 0. So this is now a quadratic, like on the last example. That's 2x squared minus 15x plus 25. So we took a third degree polynomial and divided it by a first degree. X plus 9 would be the divisor. So whenever we divide, it takes it down 1 degree. So that's the quadratic equation that's left. Oops, sorry. Then old style factoring, I'm going to demonstrate that again, and then we'll have some other strategies if you just hate factoring. You could use a quadratic formula, or you can use synthetic division. We'll talk about that. But if you view the example in the program, it's probably still going to advise you to try it by old style factoring. So just like this one, x times 1x to get 2x squared. Then I need the last times last to be positive 25. I see that I need the signs to be alike to get a positive, but I need a negative middle term. So that clues me in. I need a negative times a negative to get this positive on the end. So I'm guessing 5 times 5. That's my first thought for 25. It may work. Then I check inner, minus 5x, outer, minus 10x, and I'm lucky this time I get it the first try. So that does work to give me the correct middle term. So I'm like, yay. That is my factoring answer. This is the part for the quadratic that we factored here, but don't forget, minus 9 was also a 0, which puts a factor of x plus 9 on the front of that. Now, why is that so? Why am I changing the sign of the k value? It does change signs. We know from the formula, it says when you do synthetic division, you divide by the value x minus k. So the k value is always opposite because the negative in the formula, x minus k, means we're dividing by a k value, so it changes the sign. And the other reason is, once you get it factored, if you were looking for the solutions, just like we did a little bit in Chapter 2 when we solve a quadratic, once it's in factored form by the zero factor property, we can set each factor equal to 0. And what that does when you solve, you basically throw that term across the line to solve it, so it's always changing its sign. So the 0, or the solution of 5, looks like x minus 5 when in the parentheses in the polynomial factored form. All right, so just keep that in mind. If the k value that worked is minus 9, you're going to put x plus 9 for its factor, and so on. All right, and again, if we multiplied all this together, it should give us our polynomial. It's divided down into its prime parts, factors. All right, so that takes us to number 4. Number 4 is factoring again. We got to keep this up, factoring. So now I'm going to try 4th degree polynomial, x to the 4th. Now, if we were just trying to find a combination of 4 parentheses like this, 1, 2, 3, 4 factors, 4 polynomial that would to give me this. That would be a nightmare to try to figure that out. So it would be quite the puzzle. So we have given to us to help us get that going, and then synthetic division is an easier method than that guess and check. So our clue this time on number 4 is use k equals 2. And it tells us that is a 0, given that 0 works. And it says it works twice. Multiplicity 2 means it works twice. So I'm going to use k is negative 2. and then write down just my coefficients, making sure everything is in order as it should be. And I'm expecting a 0 remainder. So I'll work my way across, and yay, I see I do have a 0. So that worked. Now it's down to a third degree polynomial, but we still don't normally factor third degree polynomials. That's very hard to do, but once we get it to a quadratic, we do that sometimes. We could try, but I don't advise it. So what I can do once I get a 0 remainder is you can use the shortened lines. You can build off that line to do the next row. So since it said multiplicity, it means I can use -2 again, and in this second round, I will now have it down to the quadratic. You know, we talked about how if you have just the 3 terms and a 0 remainder, that's a quadratic equation. That's 1x squared minus x minus 30, and we can use old-style factoring then to do that. But say you really don't like this, that unfoiling method, you can try to just find the other zeros by synthetic division. You know, it might be hard to just guess some numbers, but you could do that. You could just start guessing some values. Maybe I think 6 works. And then later in the lesson, we'll talk about why I think 6 works. I did have kind of an idea in my head to try 6, and I was lucky there that 6 did work. But we're going to talk about how you can kind of guess some of these numbers. Well, anyway, 6 did work. Maybe I can guess -5 works. And it does as well. I get a 0 remainder. So I'm able to find my zeros by repeated synthetic division. Looking for zeros, you have to get zeros all the way down. Sorry, I ran into my other messy work. But you have to have a 0 remainder to proceed. If you don't get a 0 remainder, try a different number, erase it again. But you might prefer that method. So once we find these, there are others with the sign change. That's x plus 2, twice, be x minus 6, and x plus 5. Now another way to write that, instead of writing that twice, you'll see x plus 2 to the second. That's probably more precise way to say it. And also that helps us see what a multiplicity looks like. When you have a repeated 0, you have an exponent here showing that you know, that value is there more than once, and that's called a multiplicity factor. All right, we'll conclude this session and start up again in a little bit.